Hi, everyone. Thank you for coming. Welcome to my talk on advanced ranges, writing modular, clean, and efficient code with custom views. So I work at Bloomberg. You may be able to tell that from the slides. I'm a software engineer there, and I work in trading systems in particular. So just a little bit about me. I've been at Bloomberg since 2019. As I mentioned, I work in C++ on back-end software for trading systems. Fun fact, I was previously a derivatives attorney. So if you're interested in that, come see me after and we can have a beer and talk about that a little bit. So what's kind of the genesis of this talk? Like, why am I here talking to you about custom views? So if we step back for a second and just think of ranges in general, ranges give us a really powerful tool for making kind of readable, composable data transformation pipelines, which are reusable in different parts of the system. And the standard gives us a lot of different views and tools to kind of combine and put together to do all sorts of things. But understandably, those tools can't do everything, and they're not necessarily the perfect tool for every problem. They're not always the most performant option. But we still kind of want that composability and that reusability. And so that's where custom views come in. So when I first started looking into custom views, I wanted to take a real world problem in finance, because that's kind of my domain, and see if I could use custom views to remove some of the inefficiencies in using only the standard views. So things like extra heap allocations, copies, and inefficient iteration. And the results actually exceeded my expectations. Doing just a few kind of simple changes in some cases resulted in more than an order of magnitude improvement for these real world applications. So that's kind of the motivation. And sort of once I saw that, I started thinking about what else you could use custom views for. And they're really versatile and really flexible. So in addition to reducing latency, you could also use them to manage external state and just make your code really expressive, really maintainable, and really reusable. So that kind of is the goal, is sort of what we're working towards and kind of the birth of this talk. But what are we actually going to cover? So this isn't a beginner's talk on ranges, but we're going to layer on the knowledge. So we're going to start with a brief overview of ranges and views. And in particular, we're going to focus on what I think are their two sort of most defining and breakthrough features, which are composability and lazy evaluation. Then we're going to take a quick look at kind of what the standard provides and sort of ask us, why do we want to bother with custom views at all? You know, why do we need to do this in the first place? And at that point, we're going to go into kind of the meat of this talk, which is sort of looking at how we actually build a view. We're going to look at the boilerplate, the template machinery, and we're going to understand why all of it's there and what needs to change when we kind of create our own view. And this is with the goal of then taking that knowledge and applying it to more advanced use cases, kind of case studies. And in particular, as I mentioned, we're going to look at kind of performant views, like how can we make our systems extremely performant, and also at managing external state, because this is actually something that comes up a lot in the real world, in finance and in other systems too, like weather systems, tracking systems, all kinds of stuff. We're going to wrap up with kind of a summary of best practices and pitfalls, because as we go through kind of building a custom view, we're going to see a lot of gotchas and things that actually come up in the real world that are important to keep in mind when you're building these things, because if you don't, you could end up with very subtle bugs that are kind of difficult to debug and reason through. So with that, let's get started, and we're going to go through a brief overview of ranges. So what are ranges? So we can kind of define ranges in two ways. First is the ranges library, which is one of the 4 major additions in C++20, the others being concurrency, concepts, and modules. And we can also kind of think of ranges at a basic level as a representation of a sequence of elements that has a begin iterator and an end sentinel. And I use the word sentinel, and this is kind of new for C++20, but in reality, this could also be an end iterator, and oftentimes that's the simplest and easiest way to go. So this is a range, right? It's just a sequence of elements. It has a beginning and an end. And by the way, just a slight footnote, you don't even have to have an end necessarily, which is how we get infinite ranges. So this definition is really nice because it allows us to work with range algorithms, with views, and with range adapters, which we'll kind of define all in a second, using existing containers in the STL, because they kind of all fit this definition, like vectors, maps, lists, as well as user-defined types, so long as they kind of fit this simple constraint. The official constraint or definition that you might want to just keep in mind is that they need to comply with the stood ranges range concept. Just doing that isn't always enough for every range to work with every range algorithm. So I'm going to start putting up some code, and I believe in kind of teaching by example. So I use a lot of code snippets. Please don't try to read them all. You can if you want to, but please don't. I'll explain kind of what's relevant, and almost all of the code, other than the really basic stuff, has Godbolt links that you can kind of access later. So on the left side, we just have a range, right? We use a vector of ints, and we use a range algorithm here, which is sort. And by the way, just kind of notice here that this is a little bit different than the sort algorithm pre-ranges, right? We no longer need to pass a begin and end. And this actually returns a range back to us rather than an iterator. So we kind of pass in this vector, and this works fine. But when we try to do the exact same thing with a list, this fails. And the reason is the sort algorithm actually expects whatever's passed into it to be a random access range, which a list isn't. So even though this kind of satisfies the concept of a range, it won't necessarily plug and play with every range algorithm. So why do we care about ranges? Why are they so important? I've kind of mentioned some of this already. But essentially, in conjunction with algorithms, and especially in views, and there's a reason why it's in bold, we can make code more readable, more composable, more expressive, and in many cases, much more efficient. So views is kind of going to be the center point, like kind of the focus of this talk. And so what is a view? Just so we define it. These are basically lightweight, non-owning ranges. They support something called lazy evaluation, which we'll get into later, which allows for some interesting use cases such as infinite ranges. But the basic idea of lazy evaluation is you don't do any work, you don't do any computation when you kind of define it until it's invoked and iterated over. You don't have to use any computation, you just have this lightweight wrapper. And so they provide a window into an existing range. They use reference semantics. This is really nice because they're memory efficient, so they generally do not store copies of any elements. This is also nice or not nice, depending on your perspective, because for the most part, if you make a change via these views, they'll affect the underlying range and vice versa, unless the view is not mutable. So a notable exception to this is the transform view, for example, not mutable. And we'll actually see how that works a little bit later. And the main kind of thing, the real breakthrough feature of these is that they're composable. We can basically take multiple transformations and chain or pipe them together in a really nice, descriptive, and expressive way to make kind of things go well together. So we kind of talked about views a little bit, and we'll get into more details on range adapters later, but I wanted to really mention them here because the analogy that I kind of use is you can think of a view as a Corvette that's stuck in first gear. It can do the work. It's got kind of the logic. It can do some stuff. But range adapters is really what makes views hypercharged because they essentially, what they do is just functions that take an input range or multiple ranges and maybe additional parameters, and they transform that into a view. And this allows efficient composition, right, via the pipe operator. This is how you kind of chain stuff together. That's why range adapters are so critical. So they allow for these transformations without needing intermediate containers. So very efficient from a memory perspective and very expressive. Lazy evaluation, as mentioned, don't need to do anything until we actually iterate through. So you can kind of declare these, you can reuse these, you can use partial transformations, really flexible. And these basically have three components. We'll get into a little bit more detail of these later. But you've got the view, that's where the logic lives. That's kind of what our main focus is going to be on. Then you've got something called a range adapter object. This is sort of like a helper function. It's basically a functor that produces something called a closure. And the closure object is sort of really where the magic happens, right? This kind of holds the parameters that your view might need, if it needs any. And then it produces this view when an input range is applied to it. So this is what kind of allows us to build pipelines without any input range coming in and sort of hold those pipelines and reuse them in different parts of our code. So really powerful. You can kind of mix them together. You can think of them as like links in a chain that you sort of pull together in all kinds of different ways to make really expressive pipelines. So just kind of looking at some of the power of ranges really quickly. This is a simple example. Just have a list of numbers. We want to print out all the odd numbers. Here we're using stood remove if. Just in case anyone doesn't know how stood remove if works, essentially it's kind of moving everything that doesn't fit the predicate to the back of this vector, and then it's giving you an iterator to the new end. So, a couple things to notice, right? So a couple things to notice here, that this returns an iterator. And the algorithm also needs a begin iterator and an end iterator. So the reason this is important is begin and end, you just have to kind of remember more things, more room for error. The iterator is also really important too, because this is the reason the old way isn't really composable. You can't just pass this iterator into the next algorithm. The ranges way, as we can kind of see already, very similar. Now we use the filter view. So begin and end are no longer needed. So the code is kind of more straightforward, it's cleaner. Filter returns a range. So we can kind of pass this around. In this case, we don't do much with it, but we actually pass this to the range-based for loop. So the code is cleaner, easier to maintain, much more readable. And again, as I mentioned, this provides a lot of flexibility. We'll see kind of more of the flexibility later. Here, we already kind of see a little bit, but it's kind of constrained. And now we kind of get into composability. And I actually consider this probably the most important feature of ranges, at least for some of the use cases that I look at, because it allows for really expressive pipelines. So let's kind of start with an example. We're just going to start by talking about the data for this example. So we just have a simple struct for stock data. This has a ticker, current price, some price increase from some period of time before, and we have kind of just this placeholder for the cost to buy. And basically what we want to do here is we just kind of have some kind of threshold value, and we want to find the first 3 stocks that meet this threshold, buy 100 shares of them, and kind of figure out what that's going to cost. So that's kind of all we want to do. So this is the C++17 way. And already we can see that to do this is sort of really cluttered, right? Even kind of assuming this input data already exists. We've got lots of code here. It's very verbose. We're using extra storage to copy the results of std copy if here, as we're kind of filtering and then transforming the data. And then also notice that there's actually undefined behavior here, because we're using a for loop kind of at the end to go through these tickers to kind of print out the cost. So if there's less than 3, we might be accessing parts of this filtered data that doesn't exist. So you have a little bit of UB. So this kind of works, right? This is the output. So the first thing we want to do is fix the UB. That's pretty easy to do, right? We can just use std min here to take the smaller of these 2 things. But now this makes it even more verbose, kind of even more unfriendly. So now let's look at the ranges way of doing this. So we basically do this whole thing in one line, right? So the first line kind of creates this result. We're passing in input data right away through a filter, looks at this threshold value, then through a transform, and then we're using kind of std views take to take the first 3. And by the way, if there aren't 3, this will still work. So that UB is immediately gone. And this is really easy to read. Think about kind of how this goes. You're actually reading from left to right. So it's very kind of human focused, right? As you take the input data, first it's filtered, then it's transformed, then you kind of take the first 3. So really nice, really clean code. And notice there's no intermediate container needed, no extra storage. And this is also much safer, as I mentioned, there's no UB here. So this is a big improvement, right? And we can already see how that pipe operator, by passing these ranges through, makes things really composable and really expressive. It might be worth noting, and I kind of mentioned this already, the transform view is not mutable. So in the 17 example, just to show you, we actually are kind of mutating that cost to buy. So depending on kind of what you want, you may want to do it a slightly different way, as the transform is not mutable. You also don't have to use the pipe operator. You can actually nest these. This results in the exact same thing, but please don't do this. As you can see, that sort of like human readable view, that really kind of nice set layout that we had is now gone, right? We now have to kind of read it inside out. So you have to kind of go all the way in and figure out, oh, this is first kind of filtering, then it's transforming, then it's taking, so don't do this. So that's kind of the first breakthrough feature of kind of ranges. The other one I kind of want to briefly touch upon is lazy evaluation. So as I mentioned, lazy evaluation is kind of the opposite of eager evaluation. So eager evaluation is what we're generally used to. So in eager evaluation, what happens is we immediately calculate and store elements when something is created. So for example, if you were creating a new vector via an algorithm, or even via a range algorithm, all that calculation would be done at once. On the other hand, a lazy view, and I kind of use the word view here intentionally because it's mainly done through views, defers this computation until the elements are needed. So eager evaluation causes us to pay the cost of computation up front. These elements also need to be stored, which can affect memory usage. However, it's important to note that there are some advantages to eager evaluation. If you're going to iterate over the range multiple times, you actually might pay a higher price if you're using lazy evaluation, and we'll kind of see a quick example of that in a minute. So let's just kind of do a little bit of an experiment, to measure computational cost. This is an eager implementation of something. It's really straightforward. Just have 200 data members, and we're just doing some work. We're kind of squaring, adding 9, and then we're sort of filtering, just kind of doing stuff, basically. Notice how there's intermediate data structures created as we transform this data. Some of this could probably be optimized away, and actually notice that we're using a list. So if we wanted to, for example, remove elements in place, this would be an O of 1 operation. So it's actually relatively nice versus kind of a vector. But even so, we would need more memory than a lazy implementation. There's just kind of no way around that. And we also have to pay the computational cost as we filter and transform this data, whether or not we're going to need to use it later, right? Notice here that we actually don't do anything with it, but we still paid all of that cost. So the lazy implementation is, you can see right away, is kind of much cleaner, right? And so there's no intermediate data structure here until we load the results using CppN, right, into a new data structure. And we only care about the first 10 results. So just kind of taking a step back, why do I only use the first 10 results here? So one reason is it makes these slides work, right? And kind of makes the computation good. But there's also kind of practical reasons why we might only want to use the first 10 results. So imagine that this data, for example, is like time series data of stock trading. Maybe we're using some sort of strategy that only looks at the open, right? Maybe we only need the first 10 minutes or the first 10 seconds of this data. So lazy evaluation can work really well when we're kind of filtering or slicing data. We're not using all of it. And in this case, maybe we're using the first 10, but maybe a different strategy or some sort of analytics or something else. Maybe we'll use the next 50 or the last 50. So we kind of still have all of this data, but if we don't want to use it all, lazy evaluation could be a good option. Also, just wanted to point out, we have this kind of stood CppN here, and it's a little bit kind of unfriendly. You've got this back inserter. You sort of need to kind of know the syntax here. In C++23, we can just use stood ranges too, and now this becomes really clean and really expressive. The only kind of real difference here is in the pipeline. We immediately use the take view for the first 10 because stood ranges 2 just materializes the entire pipeline. One other thing I just wanted to note here is the vast majority of this code and kind of everything here is applicable to C++20. There's a couple of 23 things like this that I'll call out specifically. You don't have to use them. You can kind of do it other ways, but they do make your code better. So if you have access to 23, I'm sure we all have 23 for sure, then it could be an improvement. So now we're just going to kind of measure this cost, right? So all this is the eager implementation and the lazy implementation from the past couple slides, all the same. I just added a really simple test harness with Chrono. And so what do we think? Like, is this going to be good, right? Is lazy evaluation going to be a lot faster? And it turns out that it is a lot faster. So, you can play with the Godbolt link here and kind of try it out for yourselves. The numbers don't really matter, but you're sort of going to see the same pattern. And it's nearly a full order of magnitude faster with lazy evaluation, like about 9 times faster for the most part. So really, really good results if this is kind of your use case or fits your use case. So some of you may have noticed that in the lazy evaluation section versus the composability section, I actually changed the order of the views. So instead of having the filter first, I had the transform first. And sort of an interesting question might come up is, are these things commutative? Does the order of these views matter at all? And it turns out that it does. And it actually kind of matters a lot. So if you have the filter view after, you're about 40% slower than if you have the filter view first. And filters really should be placed at the start of the pipeline before any transformations. And the reason for that is a little bit technical, but the way the filter kind of view works is it takes the position rather than the value of the element. So if it passes something through, all it has is the position. And then it has to pull up to everything above it to get the value. For kind of more information on this, you should watch Nikolai's talk, Taming the Filter View. I think it's like 60 or 90 minutes just on this one topic, because the filter view is really complicated. And sort of the last thing that I kind of wanted to go over in this introduction is, we sort of mentioned this already, is what if we need to invoke the pipeline like several times, right? So this is kind of the same code. You can look at the Godbolt. The only difference here now is we're kind of using this lazy evaluation 3 times. We happen to use 45 and 70 instead of 10. And does this make a difference? And it turns out it does make a big difference. So in this case, again, lazy evaluations may be like 30 to 40% slower than eager evaluation. So again, it's a great tool. It's really useful, but it's not always the right tool. It's just one tool. So you have to kind of think about your specific domain, your use case. Does this make sense? So that's kind of the introduction. So now we kind of have a good understanding of ranges generally. And kind of the idea behind that is we have ranges, right? We can make these really expressive, really powerful pipelines, but they can't do everything. So we might want a custom view. So the question becomes, we do have a lot of standard views already. So C++20 gives us quite a few views, including some really powerful ones, like we've already seen, like the filter view and the transform view. The split view is another really popular one that people have been waiting for. And 23 gives us even more, including some of my favorite views, like the zip view and the zip transform view, as well as the Stride view. So we have all these views. They're really powerful. They're really expressive. So why do we want to bother building our own? And building our own is kind of a big project. It's hard. It's a lot of work. So why do it? And there's a couple reasons. So the first, and this is kind of what really was the genesis of this presentation and what we'll kind of explore first, is they can be used for memory and computational optimizations. In certain use cases with certain things, the standard view is just not efficient. It just doesn't provide for this use case, and we wouldn't expect it to, because it can't provide for everything. But we can build our own to make things hyper optimized. Another case is that something is just not efficiently provided for by existing views. So you might have a specific domain application or something in your line of work or in your company which you want to do, which you're going to reuse all the time, which you may want to fit into a bigger pipeline, but the views just don't work well for it. And we'll kind of see a simple example of this too. And the last thing is a lot of times we want to use external state. So external state can be really useful in many, many applications. We'll kind of see this later, but kind of in my world, for example, in the financial space, a lot of times we might be processing stocks, but we're processing them based on some external state. So for example, things like the Sharpe ratio, which is a measure of return to risk, or sentiment analysis, or all kinds of other stuff. And how do we factor that in without making our pipeline brittle, with keeping it kind of strong? So as I mentioned, kind of the genesis for this is computational efficiency. So when I thought of it, the first sort of use case I thought about, which is relatively simple, is a moving average, right? So a moving average, for those who aren't familiar, is basically like a window view that just keeps moving one over, and we're just taking the average of that window. And I kind of thought about, could we make this more efficient, right? So this is using the slide view here, and we could obviously incorporate this with other views, make it part of a pipeline. And this is actually already pretty efficient, it turns out. So slide view doesn't allocate, right? It lazily generates non-only subranges. So there's no heap allocation. Fold left is sort of for those not familiar with fold left, I kind of like to think of it as the C++23. This is a C++23 algorithm of accumulate, right? This is sort of like the successor to accumulate in my view. Is also really efficient, just walks through the elements of the view passed in. So from a computational perspective, so this is basically an O of nm, where m is the window size, and n is essentially how many windows we're going to go through, which is the number of elements minus the window size plus 1, approximately. And the question is, can we do better than this? And there's kind of an obvious optimization here. So the obvious optimization is every time we get a window, we're kind of creating a new window here, right? And then we're finding the average of it. But actually, if you think about like a sliding window, all we really need to do is keep a running sum and remove the element that kind of moves out of the window and add the new one. And that's an O of 1 operation, right? So we can definitely do better. This can be linear, and this can be done with a custom view really nicely. So this was sort of the first thing I looked at. But then I found something kind of more interesting with a little bit more inefficiencies. And this is a sliding window median value. So at first kind of glance, this seems kind of similar to the moving average, right? But it's actually way less efficient than the moving average. So the computational considerations are kind of similar here again, right? You're taking these windows, you've got to actually sort them in this case, and it's still kind of an O of nm operation because you're basically going through, you've got kind of m windows, And for each window, you're kind of taking all those elements, you're kind of copying them in. But sort of the real problem here, the real inefficiency, is that now there's a memory issue, right? So as we mentioned, the slide view doesn't do any allocations. But on every iteration of the loop, we're actually doing a heap allocation for slide data, because now we're doing a median value. So we need some kind of tangible data structure that we can kind of then sort, right, to figure out where that median is. So that's pretty bad, right? We're doing this heap allocation. We're also doing copies of all of that, right? So that's also pretty bad. And it actually turns out that slide view itself is not maybe as efficient as we thought. So it doesn't have any heap allocations, but producing those sub-ranges over that sliding window turns out to be not that efficient, actually, and has a big cost, especially with small window sizes and kind of tight loops. So this is kind of the same thing. The only kind of difference on this slide is I make this more fulsome by accounting for whether your window is an even size, but that's not really super interesting to us. The other thing I kind of want to mention here is somebody might ask, so we have this kind of slide data, right, which is using heap allocations. So a common question is, why don't we hoist this out of the for loop, right? And then we don't have to make these heap allocations. And that's true. But there's a downside to that. Actually, a couple downsides. So one downside is now you're kind of creating an external mutable state, to this particular calculation. And remember, the goal is to have this calculation be part of a bigger pipeline. So now you have external mutable state to your pipeline, which is kind of brittle. And we'll see a lot of problems with this later, right? It's also not very readable because this might not necessarily even be near your pipeline. It could be somewhere else. So that's kind of one issue. Another issue is if we ever want to parallelize it, if we hoist it out of this loop, you essentially create like a race condition. And then kind of the third reason, not so much a reason not to do it, but we'll see that we can kind of achieve this, removing heap allocations without taking any of this downside when we use custom views pretty easily. So why do it? So I did kind of want to address that first. So this supports, as I said, both odd and even windows at this point. And so before we kind of even get into the views, I just want to motivate this a little bit and show some benchmarking. So we've got 3 different implementations. We've got the standard slide view. I'm going to show a deck implementation, and I'm going to show a circular array implementation. And we're going to do this for 3 different window sizes just to kind of see the difference, and 3 sets of input data sizes. And the results were pretty good, right? So this is for 30,000 elements. And we can kind of see here with a window size of 101, for example, the array is more than a full order of magnitude faster than the slide view. The deck alone, which really just kind of removes that overhead from slide view, it really doesn't do much else, is in many cases 40 to 50% faster, in some cases even more, right, than the slide view. So we can achieve really good efficiency with not that much effort with custom views. We kind of see similar things, less in some cases here with 100,000 elements, 6 times here with 300,000 elements. Your mileage may vary. You can play around with the God bolt. Obviously, God bolt has some overhead. So don't necessarily look at these numbers. What's really more important kind of is the ratios. So now that's kind of the motivation, right? So that's kind of why we want to build a view and some of the stuff that we can do with it that makes it really powerful. So now we're going to kind of go through how to actually build a view. And the example that we're going to use to kind of motivate this is a relatively simple example, but it's actually not really covered by standard views. So I think it's kind of an interesting example. And the idea is we just have kind of let's say an array of integers, a vector of integers or whatever else, and we just want to skip every nth element. And so we could kind of do this with the filter view, right? This is a filter. So we have this kind of input data, and we can see that this works. By the way, this std print also is a C++23 feature. Std print generally plays pretty nicely with ranges. It's also kind of a good reason to use them. So this kind of works, right? Sort of, right? But we can already kind of see some problems. We've got this local counter variable. This is a mutable filter. Not necessarily great. Some people kind of immediately think of the stride view. Stride view is sort of interesting because it's actually the opposite of this. It'll take every nth element rather than skip every nth element. So there isn't really a simple way to kind of do this with the standard. But you see how brittle it is already, right? So if we try to run it twice, we now actually get bad results. And the worst part about these results, right, we're using this mutable lambda with a local counter, and it sort of persists across iterations. And that's why we're getting these bad results, right? Really bad results. And we actually don't even know what the results will be until we get them. So it's kind of undefined and just wrong. There's no good way to reset this state when you do multiple iterations. That's why we end up with this. Sometimes it'll actually work depending on what you have in your input data, which is almost even worse because then you won't see this problem until later on kind of in production. And so there's a lot of issues with this approach. It's obviously not reusable, right? How do you reuse it somewhere? You can see it's not working. Can lead to UB. And then the other problem with this is it's hard to test, right? Because first of all, to test this, how do you reset this counter, right? How do you kind of isolate it? Not great, sort of very brittle, right? We don't like this. So we're going to kind of do this with a view. So this is the overview, kind of the overlay of a view that will take care of this. So we're going to go through all of this in a lot of detail. This is sort of just the overview. And by the way, this compiles. It doesn't do anything, but it does compile. And we can kind of see the structure of this. And at the heart of this, which we'll get to in a few slides, is the iterator. The iterator is kind of still at the heart of ranges, and it's certainly at the heart of kind of views and custom views. So we're going to get into all of this. So literally line by line, right, we're going to go through this. So what's this line doing? Essentially, we're building something composable. So we're creating kind of a templated view over whatever's being passed in. So input view represents the range that's being piped into this view. And the requires clause here, it's actually not necessary kind of for what we're doing. I really just kind of wanted to demonstrate how these work. And what this says is that the input needs to be a common range. And what that means is that the begin and end iterators are the same types. Essentially, you're basically saying I'm not going to provide a sentinel, which is good practice if you're not going to provide a sentinel, which I don't. There's other common constraints that you could use here as well. So for example, random access range, right? If we need indexing, that's kind of what's happening. It's not a view, but that's basically what's happening with the sort algorithm that we saw earlier, where stood list doesn't really work in it. Or we might need forward range for like multi-pass algorithms, or really you can kind of put anything you want here. This isn't a talk on concepts, but concepts and ranges really go together. So you can kind of make this very, very descriptive, very kind of expressive to what your use case is.
Just a quick question.
Sure.
If you can go back one slide.
Yeah.
Could you have declared this instead of template standard ranges view, declare it to be a common range? A standard range is common range of input view and drop the requires clause?
I think so. I think you could have done that.
Okay.
Yeah, I think that would work.
Yeah, just checking.
So here, we're basically taking our view and we're inheriting from the view interface. And this is a really simple line, but this is actually doing a lot of work behind the scenes, like really a lot. So first of all, we have this base class and it provides us with a lot of behavior for free. So first it satisfies that stood ranges view concept, right? So what this does is it tells the ranges library and really the ranges ecosystem that this is a view. So if we didn't have that and we wanted this to be treated as a view, so for whatever reason you don't inherit from this, you actually have to enable this as a view for the ranges ecosystem. Otherwise, ranges won't see this as a view and it won't be pipelinable and it just won't work. It won't really compose. So this is giving us that for free. It's also reducing a lot of boilerplate. So you probably noticed in that overview of the view, or you will notice, there's no empty function, for example, and there's no lots of other functions because we're getting all of this for free here. We're using kind of a relatively simple like iterator, but here, if we were using, for example, a bidirectional iterator, it would give us back for free. If we were using a random access iterator, we would get the bracket operator for free, all kinds of stuff. And the way that this does that is the curiously recurring template pattern. You probably have already kind of seen it in here. And that just not to go into too much detail of that, but essentially it's a common pattern that allows the base class access to the derived class implementation. And the reason that's important is if we want to implement empty, for example, what's going to happen is the base class is going to call our begin and end functions, which are required, and that's how it's going to figure out that it's empty. So this lets us kind of tie in to the ranges ecosystem and get a lot of really powerful functionality for free, is really the CRTP. So you want to inherit from this really simple line, but doing a lot of work. So this line here, and just to kind of show you, this is in the actual main, right? This is the example. And what this does is it's a little bit magical. So you have this stood views all. And what this will do is it'll take kind of any input range and it'll make it into a view, whether it's a view or not, right? So if it's not a If it's not a view, so let's say it's like a vector, it will convert it into a non-owning reference view. If it's an R value, it'll actually convert it to an owning reference view, or sorry, to an owning view. And if it's already a view, then it'll just no-op it. So really, no matter what you pass it in, it's going to convert it into a view. And the reason we need to do this is because our adapter expects it. Otherwise, it's not going to compose. It's not going to work. So like I said, this wraps a non-owning reference view over the input vector. And this ensures compatibility when you're composing with view pipelines. So one important thing about this is we have this to kind of make the machinery work at the start, but we'll see in a little bit that we actually don't need it, because once we build our range adapter, this will be taken care of for us. Sorry.
Oh, you might have just touched on it, but I was going to say, if you don't expose a range adapter for your custom view, it's better practice to use a deduction guide to.
We'll get to the deduction guide. Yeah, we'll get to the deduction guide, and we'll have the range adapter. But yeah, for sure. So this is just temporary, but I thought it was nice to explain because this is something really powerful and useful. So now we kind of move into the iterator. And the iterator is sort of at the heart of views and ranges, really. And a lot of this stuff is going to seem like it's not important, but I think it's really worth going over because it is important. Because all of this stuff, even the boilerplate, if you understand what it's doing, it'll save you a lot of trouble down the line. Because if you neglect to include some of these, stuff will just fail, and it'll fail with really nasty error messages, and don't do that. But so these are the iterator type traits, or at least these are some of them. So the base iterator is actually not a type trait, just an alias, just makes things more convenient. The iterator category here, we see that this is an input iterator, right? So we can kind of make this any sort of iterator that we want. You know, I recommend using whatever the simplest iterator for your use case that'll work. You know, I like to start with the input iterator for maximum compatibility and then expand to other types if needed. The iterator category and the iterator concept kind of work together here. The category is the pre-C++20 category of the iterator. As I said, this is an input iterator, really simple, one-pass, read-only iterator. It's about as simple as you can get. And it helps the compiler determine which operations are valid. So for example, you know, this is an input iterator. So the compiler kind of knows that we don't need to decrement, right? This is not bidirectional. And this is mainly for backwards compatibility for older kind of STL algorithms in case these sort of plug into your ecosystem. The iterator concept is basically the same thing, but it's for the ranges ecosystem, right? It's meant for C++20 and above. And the ranges library needs this, again, to determine what operations your iterator supports. And it also will then select the appropriate algorithms for your iterator. And one nice thing is it'll prevent invalid usage often at compile time, right? So if you have an input iterator and then you're trying to do like random access, you'll get a compile time error. It won't just have like weird undefined behavior. So this is nice to have. And oftentimes this is necessary for composability, for ranges to really understand what you're trying to do. There's actually 3 more iterator type traits, all again important. So value type represents the type that the view produces when you're iterating through it. So when you're iterating through this view, what's the value type? And here we can see it's pretty straightforward. It's really just whatever is in the input view, right? That's kind of all we're taking. But this is needed for any algorithm that creates or copies values. So for example, std copy needs this, right? It's going to copy values. Even std sort needs this, right? So it kind of needs to know what this is. So you want to provide it. The difference type is the type that represents differences between iterators. So think anything that needs kind of distances or counting, right? So even, for example, std, the take view kind of needs this, and many others, right? So these are needed for all kinds of algorithms. And reference is the type that dereferencing the actual iterator gives you. Here, it's going to be a reference to the underlying range. Because remember, views are non-owning, right? They provide a window into the underlying range using reference semantics. So here, this is actually going to be a reference type to whatever is in the input view. So just to kind of bring it home on these iterator categories a little bit, many of you might already be familiar with these, but there's a bunch of different iterator types, and they kind of live in a hierarchy, right? So at the very top, you have input and output, right? These are single pass forward, and one is read-only, one is write-only. Then you have the forward, the bidirectional, the random access, and new for C++20 is the contiguous iterator category. And the way these work is as you kind of go down in this hierarchy, the iterators will have all of the functionality of everything above them. So for example, the random access iterator can do random access, but it can also go backwards, right? Because it has all the functionality of the bidirectional operator. They also have new kind of requirements on what needs to be implemented. So if you have a bidirectional iterator, then you have to make sure you implement the decrement, right? Because otherwise it won't work. So the ranges will kind of expect that you implement the decrement correctly or to whoever you want for that to function. So you get more power, but you also get more requirements. So these are sort of kind of an overview of these categories. So now we look at the actual iterator implementation. We've already done the type traits. You sort of see that you have a default constructor. For the most part, you don't actually need this, but it doesn't cost you anything to include it, and it's good practice to include it, because there are occasional times when this is declared but not initialized right away. You sometimes see this in testing libraries or other generic libraries, and so it's good to kind of have this default. It's just this line. So you should include it. The prefix operator here is sort of where the heart of our logic is. And this kind of mirrors our lambda logic from before, right? You can see that this sort of moves up the current position. It moves up this counter, which is sort of figuring out where we should skip. And then it says, oh, if we're not at the end, and if counter is the multiple of whatever we choose n to be, then we kind of skip that essentially. We also have the equals operator, relatively straightforward. Notice how we don't have the not equals operator. We get that for free. That's also kind of part of what we get by kind of using some of these helper classes. The begin and end, pretty straightforward, right? Nothing much here. I intentionally did not use a sentinel here because this is kind of simple enough that you really don't need one. But it's good to be aware that you can have a sentinel. And just to kind of expound on it just for a second, the advantages of sort of sentinels is that they don't have to be positional based, right? They can be logic based. They're also often more lightweight. So in certain circumstances, they kind of make sense. And of course, they power certain things like the infinite kind of range, right, is basically a sentinel would do that. So now we kind of put this all together, right? We built out the iterator, we built out the view kind of machinery. So we kind of create our view here with the test view, right? And this works, right? So this seems okay, right? We kind of put it all together, it's functioning, now it's actually working. But the whole point was to make this composable, was to sort of be able to plug this into the ecosystem. And so, is it composable, right? No, it's not composable. And the reason that it's not composable when we try to kind of put data into it, we just get an error. It's because we didn't provide for the pipe operator. And to provide for the pipe operator, which is kind of what we're going to do next with the range adapter, there's sort of a couple of ways to do it. If you're lucky enough to have access to C++23, we're going to kind of go through what I think is the idiomatic way. Kind of later, at the very sort of end, we're going to do a quick little bonus of how you would do this in C++20. It's not that different, but it's a little bit more manual, and it's just not as idiomatic. It's not as future-proof as kind of this system. Yes?
Yeah, so you're returning from your operator star, you're returning by value because you wrote auto, right?
Yep.
So that means that the input iterator tag is incorrect for iterator category, but not for iterator concept. And that's because the C++17 input iterator has to return a language reference from operator star. So, yes.
Forward and above has to return a reference. Input can return a value.
Yeah, you're right. I got it backwards. Thank you.
Problem solved. Thank you.
So yes, the category, if it returns by value, then the category iterator category has to be input iterator.
Yep.
Yeah.
So
the concept could be something else, but the category has to be.
Right. So the idiomatic way is to inherit from something called range adapter closure. So this is a C++23 construct. If you have it, you should definitely use it. And this works really nicely. So you kind of see at the bottom here, we have this global essentially, and it creates a new object, a skipN object. And this is what users interact with. So if you write something like view skipN3, that's kind of what you interact with. You don't have to do this way as this kind of global, but it's stateless. It's very lightweight. So it's very safe. And this is actually, at least my understanding, this is kind of how the standard does it for their views. So it's very sort of idiomatic. SkipNT here is the range adapter object that creates closure instances. And this is basically a helper function, right? You can see it's kind of like a factory. The call operator is overloaded, right? It takes your parameter here and it returns a closure. The closure, that's the object itself that holds the parameters, and eventually that'll create the view. That's kind of where the magic happens. You can sort of see that in that closure, we'll go into detail in a second, but you can see in that closure, its call operator is also overloaded. So when an input range comes in, it uses perfect forwarding to create your view with that input range, along with any parameters you might have. So when we inherit from this, again, we define this one global instance just for convenience. Don't have to do it that way, but it's good practice. Skip N3, that's the closure object that holds our parameter. And this closure object, by the way, until we send an input range to this closure object, it just kind of exists. It's like a partial pipeline, and we can kind of connect it with others or do nothing to it. It's just sort of ready to work, essentially. That operator takes an input range, as I mentioned, and returns an instance of our custom view based on that input range. It transforms that range with the parameters. And because we inherit from this adapter closure, notice that there's nothing here about the pipe operator at all. We get the pipe operator for free, right, to enable pipe syntax because we inherit from this. Unfortunately, in C++20, you don't get this for free, as we'll see, but it's not that difficult to sort of overload. So final bit of scaffolding to kind of get to your question. This is, Jeff?
Just a quick note, in C++26, you'll be able to get rid of that object as well because you'll be able to make the function operator static. And so then you don't need that object as well.
Yep.
So,
yep.
And it actually generates tighter assembly.
So this is the template deduction guide that you had mentioned earlier. And basically, this just helps the compiler determine what view should be coming in. So essentially, as the input view comes in, the compiler kind of needs to figure out, oh, what should this be? So this essentially says whatever range is coming in, make sure you wrap it into std views all, right? And kind of create our view with it. So this is really helpful. A lot of times you actually don't need it. The compiler's pretty smart. It'll figure this out. But again, this is something that doesn't hurt to have. It's good practice. Otherwise, you might occasionally end up with some ambiguous stuff. So now let's ask the same question, right? Is this view composable, right? So it looks like it now goes into, it takes the range, it works correctly. We run this multiple times, unlike the Lambda. This all looks pretty good, but is it composable? And it turns out still not composable, right? Because when we pass this into the take view, we still get an error. And why do we get an error? I kind of deliberately left something out of the Iterator implementation, which sort of looks harmless, but I wanted to kind of point out that when you're implementing this, even stuff like the iterator traits or certain functionality is actually really important to kind of think about everything that needs to be there. And you can use things like static asserts, for example, to see if you're missing anything. Because if you don't do that, you could end up with this odd behavior. So the take view actually requires the both the prefix and the postfix increment operator. And I didn't implement one. So pretty harmless, but just because of this, take view doesn't work because it's looking for this. As I mentioned, sort of depends on the postfix. So you have to kind of implement everything. Without it, composition could fail. So now, finally, we ask again, is this composable? And now it's finally composable. So that's kind of the general machinery of how you build a view. So now that we've seen this with a simple view, we can kind of expand it to more complex views for performance. So just like a quick recollection, so if we look at this, Ben?
I was going to ask, well, since you mentioned performance, did you compare the skip n with a standard way of composing views to achieve the same thing?
I didn't, just because the skip n probably wouldn't have had any performance gains, at least the way I implemented it, because I didn't build it for that. Okay. But you probably could make it more efficient in some ways.
I'm wondering if it would how it would compare with like chunk, map, take over the chunks and join, because that would be skip n, right?
Yeah, that would basically be skip n. Yeah. So kind of going back to the sliding window median value. So just as a quick reminder, some of the issues with this, you have heap allocation on every iteration, you're copying the entire window, and you have that overhead from slide view of creating subranges. So some of this stuff we want to try to get rid of. So the first kind of iteration of improving this is a deck-based implementation. So in some ways, this doesn't improve much, right? We're still going to have heap allocations, one for every window. we're going to have the same amount of copies, but the copies will come from the deck rather than from a new view. And it turns out that this is actually really helpful because, as I said, getting a new window from the slide view involves a lot of overhead. And we're going to get rid of all of that with the deck. Using the deck, how do we get a new window? Basically, we just remove the oldest element and we add the newest, both of which are O of 1 operations. So this can be kind of a very efficient way to sort of do things. So now we kind of look at the deck implementation. Some of this hopefully will start to look familiar to you guys as we kind of go through it, and that's the idea. The idea is once you understand the machinery and kind of the boilerplate of some of this, you can kind of create your own views. So this is the deck implementation. It's pretty similar, other than, you kind of have a deck, right? That's on the right-hand side. And then the other thing I wanted to point out that's kind of different here is the reference, right? The reference here is actually a value type. It's no longer a reference. And this is sort of an example of why it's important to kind of pay attention to these, one. And two, why is this a value type instead of a reference? So if we think about the CppN view, what was the reference, right? It's what you get when you dereference the iterator. And since it's a non-owning kind of window into the underlying range, you would get a reference to that type. But here, it's a little bit different because we're taking that range, the underlying range, and we're actually doing a transformation of it to get this median. So this doesn't necessarily kind of exist in the underlying range. So it actually makes more sense to return this as a value type. And again, this is sort of the same thing. In the prior implementation, we had a reference to an existing element in the underlying range, but here, since we're creating something, we actually want the value type. Doesn't exist in the range, yep. So the actual implementation of the deck is pretty simple, right? So this is the constructor. A lot of this is just checking for kind of edge cases. So if it's an empty, we don't need to do anything. We sort of fill it up with the size of our window here. If it ends up being smaller than the window size, in this case, we also just set current to end and don't do anything. You don't have to do it that way. You can implement this to work on smaller windows. Also, I didn't do this again because this isn't really a concepts talk, but you can also create kind of constraints for how this is going in to some extent to sort of prevent some of these edge cases as well. This is the dereference operator. And you'll see that this basically looks like our sliding window median value, right? Essentially, we just took that and now this is what it is, right? So we have this new vector, right, sorted. We put the window into that, right? So that's the heap allocation and the copy. And then we use std_env element, which is very efficient to find the median. And then if the median happens to be an even size, then we use max to find kind of the second half of that. So it's still a linear operation. So relatively straightforward. We're just basically putting the median in here, but we're encapsulating it in our view. The prefix increment operator, also pretty straightforward. At the very end here, you see that assuming that we're not at the end, right? If the window is not kind of moving to the end, we're basically taking the value from the front, we're taking it out, and we're adding in the new value, essentially. That's just how the deck works. So those are the two O of 1 operations that we talked about before. So that's a bit improvement. We kind of saw some of the improvement of that. But we can do better without too much more effort, right? So the second kind of iteration of this is a circular array implementation. So if we think about an array, right, to start, what's the advantage of using an array, right? A fixed size array, we're going to allocate on the stack. So immediately we remove the heap allocation. So that's kind of one big advantage. This also generally improves cache locality, right? Because an array is guaranteed to be contiguous. A deck doesn't necessarily have to be. So that's another kind of source of improvement. And similar to the deck, we avoid the overhead from the slide view, right? We're not creating sub-ranges on every iteration. One problem with this is what's nice about a deck is when we remove elements, we just kind of pop them on and off in these O of 1 operations. But typically with an array, if you remove an element, you have to shift everything over, right? That's like an O of n operation, a linear operation. We don't like that. So an easy way to kind of avoid that is to use a circular array, right? We can just kind of keep track of where the oldest element is, remove that, and kind of move that to the next oldest element, essentially. So this works really nicely because we get rid of a lot of these downsides of the slide view. There are some downsides to this still. The biggest is probably code bloat, right? So if you have lots of different window sizes, you're going to end up with lots and lots of code. And then you need to know the size of compile time, kind of related. And then the other thing this doesn't avoid is copy costs. I think there are ways to avoid copy costs. I just didn't implement them. But I think there's more kind of optimization that can be done on this iteration. This is just sort of an example of just some simple things where you can see huge returns. And so this is the circular array implementation. Again, this should start to look pretty similar. This looks almost identical to the deck. The biggest difference is now we're kind of keeping track of the oldest element here, right? So we have the oldest index kind of at the bottom. Otherwise, this is exactly like the deck. Again, we're using value type for the reference because we're creating something new here, not just looking at the underlying range. So this is the constructor for the circular array. And again, this looks pretty similar. We're doing some edge cases. We're making sure it's not empty. We're kind of filling it in. If it's smaller than the window size, we're just making a decision here to not do anything. And then we're setting the oldest element to 0 to kind of start somewhere, essentially. The dereference operator is, again, similar to the deck. Basically, this looks just like our slide view where we're kind of, but except the difference now is we're using an array, right? So sorted is actually stack allocated. So we're no longer doing a heap allocation. We are still doing the copy here with copy n. That's kind of the main source of friction here. The prefix is sort of probably the most interesting part here because this is also where we're kind of taking that oldest element in our window and we're replacing that position with whatever's coming in new. And we're shifting our oldest element pointer essentially to the next element to kind of keep track of that circle. And so that's kind of the circular array implementation. So I'm not going to show all of these again. But I did want to show this one. I did kind of cherry pick it because I think it has the best numbers. But you can kind of see some of the results here, right? With these relatively simple kind of customization points, you know, in some of these, you see more than an order of magnitude improvement. These are real differences, right? So if you're using this in like real applications that require latency and performance, these are huge differences with very little effort. So that's kind of the performant use case. The other big use case that I wanted to kind of go over here is filtering based on external state. And before we kind of go into the code and kind of the machinery, let's step back and kind of think about like why we want to do this at all. Like, why do we care about this? And, you know, in my domain, for example, in like finance, you know, you might be filtering based on a pipeline of stocks, right? You might have a bunch of stock tickers that you're filtering, but you might be filtering them based on some external criteria. You know, so we mentioned, for example, something like the Sharpe ratio, you know, which is a measure of return to risk. You know, if it's above some amount or below some amount, maybe you want to execute some strategy or you want to do some analytics. Maybe we're not using the Sharpe ratio. Maybe we're using some sort of sentiment analysis. Maybe we're using something else. Maybe we have a huge set of variables and categories of data that's constantly streaming in. And we're only kind of filtering these stocks to analyze or trade on, depending on what's in there. And it doesn't have to be finance-based. You know, think of like sensors at various parts of the world looking at, let's say, volcano data or weather data, right? They might say, oh, you know, we're going to raise an alert if the seismic activity is above some amount, right? And that amount is kind of streaming in. It's outside of your pipeline. So your pipeline basically filters it and then does some work maybe to raise an alert or do whatever. So this is kind of a very practical, like very real scenario of where we want to use external state, but we still want to use kind of the power of ranges, right? To have these deep composable pipelines. So this is kind of the starting point. So this is kind of the financial example. So we start with like a string of stocks. You know, obviously this is arbitrarily short, so we can kind of see it, but this could be thousands of tickers potentially. And for the actual external data, we're just going to use the Sharpe ratio, as I mentioned, which is just a measure of return to risk. But again, part of the reason I use the Sharpe ratio is because it incorporates lots of other stuff. In reality, this would probably be a huge data structure with all kinds of information and tens of thousands of stocks. Also notice that in the map here, some of the stocks in our vector are missing. In particular, AML, which is a London-based stock, I think it's Aston Martin, is particularly missing because I wanted to make sure that this is also robust enough to deal with the situation where data is not available for every possible thing in your pipeline, which is also kind of a common use case. So let's kind of think about how we can filter with this, right? So obviously, when you filter, the first thing that comes to mind is the filter view, right? So we're going to pass in this stock data here by reference, and that's a choice. You could do it by reference. You could also do a snapshot of it and take it by value. there's like upsides and downsides to both, and we'll kind of actually see both. But here we're doing it by reference. So we're sort of passing this in, and this seems to work, right? This works fine. But now your filtering condition is actually tied to external state. And in some ways it's even worse because it's mutable external state, right? So the encapsulation is completely broken. The filter logic depends on variables outside of the pipeline, which creates kind of a lot of problems, right? These are hidden dependencies. So you actually do have dependencies on this stock data, but they're all implicit dependencies rather than explicit dependencies. They're all kind of hidden. And the problem with hidden is all sorts of stuff. So for example, testing is really challenging, right? This requires you to set up both the state and the pipeline to test. Really difficult to do unit tests with this stuff. Also, again, we're only seeing one view here, but if this is part of a bigger pipeline and there's some issue, how do you debug this? You've got to open up this closure in the Lambda and do all kinds of stuff. So not great. We also see, and this is kind of the thing about it being passed by reference. So remember, this is lazy, right? So we create this pipeline, nothing's happened. So now if we update the stock data in between creating the pipeline and traversing it, we're actually going to get this different result, right? Apple is now below this threshold, so it no longer comes up. Maybe you want that result, but it's definitely something to kind of think about, right? That this execution happens at traversal, not at creation. That state can change, and it can create all kinds of non-deterministic behavior. It can be very dangerous because it's coupled to this external timing. And again, this is a simple example, but you could think of this as streaming data coming in constantly and constantly changing. So custom views actually don't resolve this particular problem. If you pass this in, go ahead.
I just want to say in this example with the mutable stock data, it's actually ill-formed by construction because filter requires a regular invocable function. That's a semantic requirement.
So I think the function here is actually what's in the Lambda for filter, like the predicate, right? You're asking about the predicate?
Yeah, the predicate for filter, part of predicate requires regular invocable. That's a semantic requirement.
Oh, interesting. Okay. So another kind of problem is the compiler doesn't complain about that.
It can't resolve the semantic meaning of the regular interview.
Yeah. So yeah, not great. Another reason kind of why this is not great. So views don't really resolve all of these problems, but the biggest kind of thing that they do in this sort of case is they make all these dependencies explicit, which makes them easier to test and kind of easier to deal with, and sort of you don't have some of these semantic problems. So this should all be really familiar by now, right? Again, this is the overview for this kind of view, right? For the stock threshold view. And just one thing to kind of note here, and this will become important later, is the stock data is coming in by reference, right? And you guys will see why this is important, sort of relevant in a couple slides. So kind of the main sort of logic here is actually in a helper function, right? We're just looking for the next valid kind of element. And while we're not at the end, we're kind of taking this stock. And if it's part of this external data and it's above some threshold, then that's good. And if not, then we keep going, right? Until we find the next valid element. This basically is going to be used by the constructor and the increment operator to skip any invalid elements, right? It also filters everything out, as I mentioned, either no data or things that don't meet the threshold. And we make sure the iterator is always pointing to the next valid element. So this is actually the constructor and the prefix. And you can kind of see how they work. They're pretty simple, kind of instantiate the variables and then just call this find next valid helper. So pretty straightforward for the constructor and the prefix. So using the view, right? So this is kind of where things start to get like a little bit interesting, right? So we use the view. Again, this is much cleaner, right? So you don't have the semantic issue now because you're kind of using this custom view. So that's one upside for sure. And you can see also that it's still lazy. So even here, as we update the value of Apple, it kind of removes it from the pipeline. So you may or may not want that. So the downside to not using by reference is this struct, this external data could be humongous, right? So you're making a big copy if you're not using kind of reference semantics. But the main kind of point, at least for this slide, is that state is now encapsulated in the view. And this is a big deal because now the pipeline is much easier to test, right? You can kind of reason about this easier in terms of testing, you can kind of set this up all in one go, right? It's very easy to mock this for unit tests. And because everything is isolated, it just makes it much easier to test. It's also much easier to debug, right? Because we don't have to go through the Lambda kind of closure if there's something wrong, right? We can use kind of more standard debugging tools. So it's much kind of cleaner to deal with if there is a problem or some other issue. And now it's also reusable, right? That Lambda isn't really reusable. Whereas here, we can kind of use this all over the place. And note that here we pass in this stock data. But we could use this somewhere else, this view, and pass in stock data 2 or stock data 3 or meteorological data 1 or whatever you want, right? So it becomes more testable, more debuggable, more reusable, just very robust. And just to kind of hammer this point home, this is just like a little chart about kind of the differences in these major categories. So again, encapsulation with the custom view fully encapsulated, you're not separate, it's not brittle. It's also very reusable with the custom view, with all kinds of different ranges and even different data sources. Whereas with the Lambda, you have to write new Lambdas every time you're going to use this, right? And they're all kind of brittle. For testing, again, this view can be set up in isolation. Whereas for the Lambda, they have to be set up separately and correctly. So much harder to test. And as I mentioned, debugging with a Lambda, you might have to go into that closure. So it's a lot more painful. So this is kind of a real problem that I wanted to touch on. And it's actually one of the reasons that I had this by reference, even though it's kind of weird to have it by reference because of that undeterministic behavior if there's a change. Because it turns out that, so at the very kind of top of this slide, you see that if you take some data range, these stocks, you pass it into the stock threshold view, and then you pass the result of that into the take view, this works. This is totally fine, no problem. But if you try to do it all in one line, it actually fails with a pretty nasty compiler error. And this is sort of like a real thing that happened to me. And I kind of looked at this for a long time. And basically, my understanding, and if there's any experts, by the way, after this slide, maybe you can give kind of more context. But basically, direct composition fails here because the compiler evaluates this pipeline as a single expression. And when that happens, this forces template constraint checking on all the components at once. And it turns out that these constraints for kind of the pipe operator are very conservative and very hard to meet. And in particular, what it's looking for is it wants it to be not just copyable, but safely copyable and self-contained. So when it holds external state by reference, it seems to fail this check. And so direct composition fails. But when you split up the pipeline, it actually delays template resolution, and it allows these types to pass the concept checks because they become looser and kind of easier to get through with this splitting and kind of this delay. So this fails, right, with this reference. But as soon as I change it to capture by value, no other changes whatsoever, this works, no problem. So this fails, this works, just purely going from reference to capture by value. And yep, go ahead.
Could you also fix it by changing your implementation to store the reference as a pointer rather than a real reference?
I tried that. It still did not work.
Okay.
But yeah, there might be some way to change it. I definitely tried for a while. I may have missed the secret sauce is on that, but it was like a weird kind of error that sort of still is kind of a bit confusing to me. But by value, it works, even with direct composition. And basically, my understanding is when you capture this by value, it makes the view safely copyable and self-contained. And that's why this works. It kind of likes it. So the point kind of, I guess, is owning the data avoids concept failures during composition. The downside is, as I mentioned, we use this small struct. It's very small, but a big struct can be very, very expensive. Yep, go ahead.
Yeah. So a view is allowed to be order one copyable or non-copyable and order one movable. So if you own your data, you should you should delete your copy operations.
Oh, I see. So in other words, if I could have changed the implementation to have no copies at all, then it would have passed that check.
Possibly. I don't know what that error was, but I'm just saying when you said that by owning the data, you made it copyable.
Yep.
That does work, but
yep.
It just can't tell that it's not order one copyable and you've broken the semantic requirement.
Gotcha. Yep. Makes sense. So copying this external state can be expensive. Again, this struct could be humongous. So step-by-step composition can be a reasonable workaround if that's a concern. So that's kind of the majority of this. There's a couple more things I want to go over. So first, kind of some best practices. So when does it make sense to build custom views? So we've kind of gone over this, but just to hammer it home, when standard views don't cleanly support your use case, and that could be domain-specific logic, right, where you work in finance or you work in weather or geology or just whatever you do, the view just doesn't exist. It's not efficient. It's not clean. Again, domain-specific logic. You also want to create something that's reusable. A lot of times you can kind of jerry-rig what you're doing using either a filter or just not a view at all, right? You just can do it in kind of clean code. So think of like the moving average, right? The moving average, you don't need a view for that. You don't even need a standard view, right? That's easy to kind of implement. But the whole point is if you want to use reusable things, composable things, then you have to use these views. And so you might want to use a custom view if it fits. And then also to encapsulate external state, as we just sort of saw, this makes it much more robust and much less brittle rather than the standard views, which often can't accommodate it. And finally, optimizing performance critical code paths where custom logic can outperform the standard solutions. So like sliding median. Some things to keep in mind when building these views, be explicit about writing out these iterator traits. If you miss some or if you write them incorrectly, it might work out, especially with simple use cases, but you might also end up with a lot of problems, especially when going through composability. And ensure this kind of goes hand in hand with the first thing. Make sure the iterator satisfies all the requirements for its category. So if you're building, a random access iterator, make sure that you kind of support everything that a random access iterator should support, including everything that a bidirectional iterator should support. Otherwise, this can cause bugs, especially in composition. Composition can be very brittle. The STL has very kind of strict constraints on what is composable. And if your view is meant to be composable and you're using external state, you should at least consider capturing by value if it makes sense kind of from a memory perspective, because it'll probably be a lot easier to kind of avoid some of the issues I ran into with composability. Because again, the standard assumes views are self-contained and copyable. And if your view does depend on external state, make that dependency explicit in the API. And that's basically what you're doing by creating this external view. You're essentially making the API of your view very explicit. You're telling the users that we depend on this. They have to pass it in, rather than it be hidden in a Lambda. If you happen to have C++23, please use the range adapter closure. This just makes your life a lot easier, just a lot cleaner. And then last kind of best practice here is keep your implementation as simple as you can, because these things are already really complicated. So the less kind of stuff you can squeeze in there, kind of the better. Some things to watch out for. Views are non-owning. So you should try to make sure that the underlying range outlives your view. Otherwise, you could end up with dangling references. So if you think that this could be a problem, use something like std_ranges2 if you have access to it, or something else to materialize the view into owning containers when needed. Otherwise, you might try to access something that's not there and end up with bad stuff, basically. And then also remember, pipelines are reevaluated every time they're traversed. So if you're going to have a pipeline, the same pipeline that's reevaluated every time, maybe you don't want to use kind of lazy views. Maybe these actually don't make sense for you, because this can end up being significantly less efficient. And then another thing is custom views, as we saw, they don't necessarily compose as effortlessly as standard range adapters. With the standard, if you stick to those views, they work amazingly, right? They're so simple, they're so straightforward, so clean. These require more work. So make sure it's worth it, because it's not quite as straightforward. And then kind of mention this a few times, but be careful if you capture external state by reference, because it can cause like weird failures, especially in like direct composition. Similar here, pipelines can fail. Make sure your view is copyable and self-contained. And so one kind of last thing I wanted to go over, I mentioned this towards the beginning, but we talked about the range adapter closure, right? So if you have C++23, use the range adapter closure. It sounds like it's getting even better in C++26. But if you are in C++20, like I imagine many of us are, if we're lucky, there is a workaround, and I think it's not that bad. So you can overload the pipe operator. So this kind of looks similar, right, to the range adapter closure. It's really not that different, right? You sort of have this factory function here at the bottom, right, which is skipN. And this returns a functor, right, which is skipN fn essentially. And that holds your parameters. And you can see that the call operator, again, is overloaded. So this uses std_views_all to kind of wrap whatever the input range is with perfect forwarding and any parameters you have and kind of return your view. So basically, when this is called, right, so if you were to do like views, skipN view 3 or whatever, this would return this functor. And the functor would have your, n equals 3 kind of saved. And then when the input range was sort of passed into it, this overloaded call operator would be called, and it would create your view, essentially, transformed with that input range as well as any parameters. The other thing you see here is relevant is the thing kind of halfway towards the bottom, and that's the pipe overload. So you do need this in C++20 because you don't have something that'll do it for you. It's relatively straightforward, right? R is just the input range on the left-hand side of the pipe. Fn is that functor, right? That's returned from view skipN. So if you have data pipe view skipN, the right-hand side will be that functor, and it will take R, which is the input range, perfect forwarding to your view, transform the data, and kind of return this. Go ahead.
You're actually missing one pipe operator, and that's why the range adapter closure is necessary, because there's no easy way to detect whether something is a range adapter closure, and the range adapter closure in C++23 provides substitution failure for composition of adapters into a single adapter.
So it's actually surprising that I'm only missing one pipe operator, because what I was going to mention is when you overload these pipe operators, right, I just overload this just to kind of show kind of how it works. But the reality is, kind of as you mentioned, there's actually multiple pipe operators, and they can be complex, and it's not always clear exactly how you overload all of them, which is why you want to use the range adapter closure, because it does all of that for you. Here, you're just kind of opening up yourself for mistakes. So this works, but not perfectly, and I'm surprised it's only one. Yep, go ahead.
I'm pretty sure this isn't portable. I'd have to look to be sure, but I believe it's a Microsoft implementation that their pipe operator, well, when I say it's not portable, what I mean is that this will work for you piping your skip on the end of something else, but then as soon as you try to take one of the stood views and pipe it on the end of that won't work, because the closure that Microsoft uses actually multiply inherits, or maybe it doesn't multiply inherit, but it inherits from this tag type that basically says, hey, I'm a closure object, and if it doesn't pick that up in the next pipe operation, it'll basically refuse to do the pipe operation.
Yeah, that's definitely possible. This is kind of like a hacky solution, right? If you don't have anything else.
So there's a Boost library that will do this for you. It's Boost STL interfaces, has a range adapter that works for pre-C++20.
That's right. So that's kind of this I guess workaround for C++20. But if you have 23 or later, you should use the range adapter closure. It'll make your life easier. You won't have to think about any of this stuff, and it's just cleaner. And it's also with the STL kind of idiom. So kind of future things will work cleanly with it. Whereas with this, probably won't. You'll probably have to refactor at some point anyway. So that's kind of the end. Jeff?
So back to your performance case, I'm wondering if cache last, which is a C++26 view, would actually solve the problem with slide, because it would essentially capture the slide state, so it wouldn't have to be recalculated. I mean, are we basically getting into the problem of, transform filter, where you have to recalculate the transform every time you need to redo the filter, and so you can't calculate the transform on the same element twice? Yeah,
pretty much. I think it could, because at least that part of the inefficiency, right, creating that new subrange is, I've shifted over one element, I have to make a whole new subrange, even if the window is 100 elements.
Yeah. So
I think it's something like that could solve it. But then there'll be another problem, right? So I chose this example because it doesn't work with today's views. There'll be some other example that doesn't work with C++26 views. Go ahead.
There's another subtlety with input iterator, which is I think what I was conflating the first time I raised my hand, which is that I believe it's input iterator. It's the iterator category rather that we don't define it at all if the iterator category would be input. Like if the view that you're adapting is an input view, an input range, we don't define that in the subsequent view. So if you look at like filter view and transform view, they both do this. I don't remember the reason why, but I think that's the case. And there's another subtlety, which is that in the post increment, you should return a void in the input iterator case. Because the view that you're adapting, if it happens to be an input iterator, there's no guarantee that it's copyable. Its iterator is copyable.
So these rules are if the input view, the templated input view, is an input iterator.
Yeah.
Is that right?
Well, the thing about returning void is only for that case where where your view's iterator is claiming to be an input iterator, then its post increment should be void returning. And then the same thing for not defining the iterator category.
Oh, interesting.
And again, I don't remember what the reason is for the iterator category part, but the reason for the other one is that if you try to return, if you make a temporary and then try to return it from the post increment, if it's a move only input iterator, that won't compile. Yeah.
Oh, interesting. Good to know. Go ahead.
I was wondering in your example with the sliding window, there you are using nth element on the array, and doesn't that sort the array?
Yeah.
So how do you keep? So you have to keep track on the index.
I thought
Yes.
you made a copy.
So I made a
Ah, you
copy.
made a
That's
copy.
why you have to make a
Okay,
copy. Yeah.
okay.
So there's probably a better way that I just didn't take the time to think of, where maybe you don't have to make a copy and you can do some funky.
Nothing
You
is
know,
coming to mind.
Nothing comes to mind, but maybe at some
I
point.
don't think
But
there's a better way without keeping state that
yeah.
flows between.
But maybe
iterations.
there's a way. Someone actually mentioned to me a few days ago. There might be a way, for example, to have another array maybe on the stack that somehow keeps track with pointers of where stuff is. But I don't know if it's worth it or if it would work. Sir?
Of elements where it keeps the index, and then you can look where it got shifted.
If you want to keep a median, you can keep a min heap and a max heap,
Okay.
right? And then the median's in between the two tops of the heaps.
Yeah, there definitely could be ways to optimize it. Nothing immediately comes to mind, but I bet there's ways for sure.
Well, so I think at this conference we talked about, could you create a sorted view that doesn't modify the underlying range, and that is something you could do. You would still have to have, storage, but the storage would essentially be, an index of the locations within, the
Yes.
range, in the order that they would be sorted. And so that's a technical possibility. Whether that's a good idea or not is another question.
That's basically kind of the idea that was floated, to avoid the copy, because that's really the last piece that's sort of really inefficient that's still there.
I mean, in the case of like integer numbers, it's probably not going to save anything, right? But if it was something, well, maybe with floating point you'd save a little bit, but because you'd still have to have essentially an array of the size of the sliding window. Right?
That's right. Yeah. Any other questions? Cool. Thank you very much for coming.
Thank you.